Every time you flip a light switch, you're witnessing the solution to a problem that nearly destroyed quantum physics. In the 1940s, the best minds in physics were getting infinity as an answer to simple questions, not large numbers. Infinity. The mathematics was screaming that their entire theory was broken. The equations that should have explained light, electrons, everything we see, were producing pure nonsense. And then one man figured out why the infinities weren't a bug. They were a feature. This was quantum electrodynamics, the theory describing how light and matter interact. It should have been our most fundamental theory. It described everything from how atoms hold together to why the sky is blue, but every calculation produced infinity. The theory was beautiful in principle, but completely useless in practice. Here's why. The quantum vacuum is not empty. It seethes with particle-antiparticle pairs popping in and out of existence. An electron moving through space is constantly surrounded by this cloud of virtual particles. Virtual photons emerge from nowhere, split into electron-positron pairs, then recombine and vanish. These processes happen at all energy scales, down to arbitrarily small distances. When you try to sum up their contributions, you're adding infinitely many, infinitely large terms. Infinity times infinity. Mathematical chaos. Physicists could see the infinities appearing in their calculations. Some thought quantum field theory was fundamentally broken, that we needed to abandon it entirely. Others tried mathematical tricks to make the infinities disappear. Nothing worked. The infinities kept coming back like a disease we couldn't cure. Then Schwinger did something radical. He didn't try to eliminate the infinities. He accepted them. He recognized that the infinities were telling us something profound about measurement itself. His key insight: we never measure bare quantities. We always measure dressed quantities. Consider an electron. You think it has some intrinsic charge, some fundamental value existing independent of everything else. Wrong. An electron is never isolated from the quantum vacuum. The moment an electron exists, it polarizes the vacuum around it. Virtual particle pairs appear and rearrange themselves in response to the electron's charge. Negative particles are pushed away, positive particles pulled in. This creates a screening effect. When you measure an electron's charge in your laboratory, you're not measuring the bare charge of the electron itself. You're measuring the effective charge after accounting for all this vacuum polarization. The charge you measure already includes the effects of infinitely many virtual processes. And here's the crucial point. That measured charge is finite. It's the value we've determined experimentally. Schwinger realized we should stop trying to calculate bare quantities and instead calculate measurable quantities directly. The infinities appear when you ask about bare electron charge or bare electron mass. But those aren't physical. You cannot measure them. They're mathematical ghosts. What you can measure is the renormalized charge and renormalized mass, the effective values that include all vacuum effects. This procedure is called renormalization, and Schwinger was one of its architects. You absorb the infinities into a redefinition of parameters. You start with equations containing bare charge and bare mass. These are infinite, but you systematically replace them with measured charge and measured mass. When you do this carefully, following precise mathematical rules, the infinities cancel out. What remains are finite predictions for observable quantities. This sounds like mathematical trickery, Many physicists thought exactly that. How can you just hide infinities inside a redefinition and claim victory? But Schwinger showed it was far more than trickery. It was a deep statement about the structure of quantum field theory. The theory doesn't predict the electron's charge from first principles. That's fine. We measure it. But once we input that measured value, the theory predicts everything else to arbitrary precision. The first major test was the anomalous magnetic moment of the electron. Classical physics predicts that an electron in a magnetic field should have a specific magnetic moment. But quantum mechanics modifies this. The electron's interaction with virtual photons changes its magnetic moment slightly. Schwinger calculated this correction. The calculation was brutally difficult. He had to evaluate diagrams with loops, accounting for virtual photons being emitted and reabsorbed by electrons. He had to handle the infinities carefully, applying renormalization to extract finite results. When the calculation was complete, he found that the anomalous magnetic moment was proportional to alpha divided by 2pi, where alpha is the fine structure constant, approximately 1 over 137.